We want to prove that 3 to the k minus 1 can be written as the sum of two squares for infinitely many positive integers k. I'm going to dive into a solution here. We're going to be using an identity which you may have seen if you've done problems like this before, where you're trying to show that something can be written as the sum of squares. It's this identity here, that a squared plus b squared times c squared plus d squared is the exact same thing as ab plus cd squared plus AC minus BT squared. So you can just verify this by expanding this if you've not seen this before. It's not super exciting, so I'm not going to do that here. You're just going to have to trust that these two things here are the same. But why is this useful? Why is this identity at all useful for this problem? What this says is if you take a number, this first number, which clearly can be written as the sum of two squares, it's a squared plus b squared, and you multiply it by another number, which also can be written as the sum of two squares, namely c squared and d squared. If you multiplied those two numbers together, you produce this number, which itself is clearly one square number plus another square number. So this means if you take any two numbers which can be written as the sum of two squares, multiply them together, this new number that you generate can also be written as the sum of two squares, which is pretty cool. In other words, the set of numbers which can be written as the sum of two squares is closed under multiplication. Okay, how do we use this here? Well, we're going to make an observation about 3 to the k minus 1. We're firstly going to find one value of k, which, when I plug into 3 to the k minus 1, that can be written as the sum of two squares. And it's not too difficult to do that. In fact, we can just use 3 to the 1 minus 1, which is 2, which is 1 squared plus 1 squared. Not super exciting, but it works. Okay. In fact, what we need is one where this power here is even, and we'll see why in a second. So in fact, I'm just going to use 3 squared minus 1, which is 8, which is 2 squared plus 2 squared. So that works. I mean, 3 to the 1 minus 1 works, but I need one where it's even. Okay, great. How do I proceed here? What I'm going to do is look at 3 squared minus 1, which we know can be written as the sum of two squares. In fact, I'm going to write it as 2 squared plus 2 squared. And what I'm going to do is multiply that by 3 squared plus 1. So this thing here, remember, is just 3 squared minus 1. And then this is 3 squared plus 1. So I can just use the difference of two squares to expand this. And this will be 3 to the 4 minus 1. Okay, why is this useful? Well, I can use this result here. And I know that this thing is 2 squared plus 2 squared, so the sum of two squares. And this thing here is the sum of two squares. It's 3 squared plus 1 squared. And so that tells me that 3 to the 4 minus 1 can be written as two squares added together. I don't know what they are. I mean, I could work them out. I'm not too interested. But it can be written as x squared plus y squared, where x and y are integers. Okay, cool. So that means that 3 to the 4 minus 1 can also be written as the sum of two squares. Maybe you can see where I'm going with this. We're next going to look at 3 to the 8 minus 1, which is 3 to the 4 minus 1 times 3 to the 4 plus 1. Okay, what can I say about this? Well, 3 to the 4 minus 1 we know is x squared plus y squared. And 3 to the 4 plus 1, well, that's just 3 squared plus 1 squared. And again, I can use this result here because I've got a number that can be written as the sum of two squares multiplied by another number which can be written as the sum of two squares. And so this equals, let me call it x2 squared plus y2 squared. And I've generated another value of k, so k equals 8 works. In other words, 3 to the 8 minus 1 can be written as the sum of two squares. And I can continue with this and do 3 to the 16 minus 1, and 3 to the 32 minus 1, and 3 to the 64 minus 1. In fact, 3 to the power of 2 to the n minus 1, using this kind of process, you can prove it by induction. This will always be able to be written as the sum of two squares. And that solves our problem. I hope that is a pretty nice solution. I think there may be a couple of other ways to do this, but I think this is quite nice. Notice that it doesn't mean that for every value of k, you can write this as the sum of two squares. But no, what's interesting is that it doesn't have to be powers of 2. So for example, if I look at 3 cubed minus 1, that's 26. And 26 is 5 squared plus 1 squared. So there are other values of k as well. This just proves that there are infinitely many. Anyway, thank you so much for watching. I'll catch you in the next one. Have a great day.